Well, good afternoon, everyone, and welcome to today's webinar, Avoiding Warranty and Liability Threats Associated with Luminaire Designs. My name is Rob Romanowski, and I am the Director of Operations for 3HTI, as well as our sister company, 3DS Man. And I'm very excited about today's webinar because we have our guest, Boris Marovic, who is a CFD expert and has been with Mentor Graphics for over 9.5 years, is going to review with you today some of the issues and challenges with LED lightings and designs and show you a little bit about how to overcome those designs with a great product that we represent for 3HTI and 3DS Man, Mentor Graphics Flow EFD and the LED extension. So glad you could all join us today. A couple of housekeeping items. We are going to have everybody on mute during the webinar, and we will probably go about 25 minutes total with a handful of slides and a demo. And then we're going to leave 5 minutes at the end for questions and answers. So if you have any questions during the webinar, please type them in ahead of time. We will answer them at the end, but if something's pretty hot and pressing on your mind at the time, just feel free to type it in, but we will definitely get to all questions at the end of the presentation. So what I like to do real quick is I notice on the line today are quite a few customers of 3HTI, but also some people that we're not necessarily familiar with. So let me take about maybe 90 seconds and go a little bit over about what our focus is and who we are. So our overall goal, what kind of business are we in? We're in the innovation business. What we do is we help our customers innovate a better product. We want to help them make a product, improve the products that they have. We want to increase their efficiency so they can make them faster and also maintain more of a competitive advantage in the marketplace and also increase profitability through that process. Ultimately, that's going to help people live a better life if they have less stress because we can help them overcome some obstacles within their manufacturing processes. Then we've done our job. We want to be a partner, not a peddler of software or any other engineering services or anything else. And this slide shows this is what this is how we help our customers through basically all types of software, services, and 3D printers throughout the discrete manufacturing process, from design through manufacturing, and also through the retirement or end of life cycle for a product. So we also offer engineering services in all phases of design, especially and including with analysis. Quick overview of our product portfolio. Not only do we represent Mentor Graphics line of the mechanical analysis solutions, but we're also a reseller for 3D printers for Markforged, which makes a carbon fiber 3D printer, EnvisionTech, which has very high precision 3D printers and bioplotters, and other solutions from PTC for design, for CAD design, for product lifecycle management, and also for high-end analysis, a product called Simulia, which is from Dassault Systems, which a lot of people may have formerly known as Abacus. Here's a host of our customer base. And it doesn't matter what size our customers are. Basically, what we want to do is we want to solve problems. We want to care about your problem and help you figure out a solution to it. And one of the customers that's on here that's kind of interesting is this company called Rab Lighting. So from 2013 to 2015, Rab Lighting was named one of the top 50 fastest growing companies in New Jersey, and we've been doing business with Rab Lighting for several years, probably at least 5. So anyway, we're excited to see their growth and their progression, and one of the things recently that we had partnered with them with is their desire to double the amount of new products that they would introduce on a monthly basis. So with that goal and that desire, we are helping them achieve that goal. So we're very excited to be able to do that for them, and also if we can do that for you as well. So what I'm going to do at this time is pass everything over to Boris. As I mentioned, Boris is our main presenter and guest today, and he has a very familiar with issues in lighting in all areas, from automotive lighting, LED lighting. So I'm very excited to see what Boris is going to present today and hear him. So Boris, I'm passing control over to you. Take it away.
Thank you, Robert. Yeah, I hope you all can see my slides. So just a quick introduction to myself. My name is Boris Marovic. I'm the technical manager of FlowFD products. I studied aerospace engineering at the University of Stuttgart. Was at the beginning an application engineer for FlowFD at Mentor Graphics. From 2010 to 2016, I was the industry manager for automotive and transportation, where I did a lot of work with the automotive lighting industry, so a very familiar subject there. And since August, so not so long ago, I've became the technical manager for the FlowFD products. And yeah, let's just start right into it. So we're going to have a quick look on the avoiding warranty and liability issues, so anything that came up in the recent years, where you can see how thermal issues basically can really cause large issues for companies with recalls and even revenue issues through that. FlowFD has a CAD-embedded CFD approach, what that means and how that works. And we're going to look at why FlowFD is so good for the lighting thermal simulations. So we're looking at CFD technology, the FlowFD technology, as well as specific lighting capabilities of FlowFD. A quick demonstration of FlowFD, so just to see how it works, how it runs inside Creo in this case, as well as then some conclusions and a few additional information that you might want to look at based on our website. Okay, yeah, I mean, warranty and liability issues can really stretch into millions due to kind of burnt down houses or even human casualties. Of course, that's something that we really want to avoid. Costs can also be in billions, considering revenue losses. For example, I mean, the Samsung Galaxy Note 7 is a good example. That's not related to failing of LEDs, but I hope they can recover from that, because I really would like to have the Note 7, but I don't think that it will be released anytime anymore. Then, of course, the damages to the company, the image or the product range, just like I mentioned, the Note 7 is probably not to come out anymore. So that basically product range is completely scrapped then. And yeah, we really want to avoid that. There are some cases that we had in the recent years, something from Cree, for example, which you can also find on the website, where they had really failing LED replacement bulbs. In this case, it's a T8 replacement bulb, and basically really caused overheating and melting, and therefore can pose human burning hazards. And if you look at how many they have recalled, it's 104,000 in the US, an additional 8,500 in Canada. Considering the cost of replacing them and also the whole management and the image issues that you get from that. We have a similar case here with Osram. They had a similar, or basically the same replacement bulb, a T8. But they also mentioned about overheating and melting that might cause potential burning hazards. Or another one, it's just another slide here. Yeah, they basically had a larger recall for Cree than for the Osram one, but the problem here was not related directly to the LED burning, but to some interconnect on the PCB that might have caused in high temperatures. I mean, that, for example, can result into joule heating issues. I can show you a picture of how FlowFD can help you with that later. Another cause here for it was Lighting Science Group, where they had 600 units, I think 600,000 units involved in this, and it caused even burned carpets, rugs, or floors, as well as lighting sockets and the melted fixtures. So yeah, worst case, it really can cause a whole house to burn down if you don't notice it or notice it too late. In this case, of course, we're lucky that there were no persons injured. Now, let's have a look at FlowFD. FlowFD is CAD integrations into CATIA, Creo, or Pro Engineer, as well as Siemens NX. And there's a standalone version where you can basically load either native file formats, for example, from Painter or SolidWorks and Solid Edge, but you can also import via STEP, IGES, or Parasolid if you don't have a CAD license on your workstation. So there is no need to transfer any geometry from the CAD to the CFD system, except, like I mentioned, in the standalone version, if you need to transfer it there. But for the CAD integration, the CATIA, Creo, or NX, you don't have to have any CAD transfer from CAD to CFD. The geometry change is directly detected, so any change that you do, the simulation is automatically synchronized with that. So you can immediately run a simulation again. You might have to update or apply additional boundary condition to that component, if that's a new component, but it's already in the simulation, it's already recognized. You just have to start the simulation again. It has an automated fluid volume detection. That means you don't have to export the fluid volume to the CFD software. If you have an internal CFD case, you just place a lid on the inlet and outlet, and everything in the inside, which is hollow, is basically fluid volume. If you consider anything externally, like a lamp in the ceiling on a room, then the whole empty space, basically, which is not a solid in the CAD system, is fluid volume. For the analysis input, so preprocessor as well as a post-processor, it's all inside the CAD system. So you don't leave at any point the CAD system. You're completely working inside of the integration into the CAD systems. Then it is very easy to use for the designers specifically. That's why we built it inside of the CAD system. And we implemented a lot of technology in order to reduce the usual numerical know-how that you need to a point where you just have to set up boundary conditions and at some point judge if the mesh is good enough. But that's something that you learn in the training, what you have to look for. And usually the training takes about 2 days where we can say, okay, now you're ready to run your own models and you can go ahead now. It leverages the CAD embedded approach by really using the detailed geometry information of the CAD system and then automatically and efficiently mesh and solve the geometry. In the next slide I'm going to show you a little bit more about how FlowFD works with the meshing and the technology, how we can make it so easy to use. But first let's have a look on how it usually looks like in a CFD, traditional CFD process. Is you start with a CAD tool, then you have to give it off to the CFD experts who run the CFD simulation. This process can be a few days up to a few weeks or even months, depending really on complexity of the model, and of course, I mean, how fast they can get to your model if they have a large set of simulations already waiting for them to work on. So this then repeats and repeats and repeats until you get where you say, okay, now we basically achieved the most out of the model, improved it to the limits, and it can go into manufacturing. Now with FlowFD we can shorten that whole cycle by doing the simulations directly in the CAD system. The meshing is completely automatic. That means usually you have to spend a lot of manual time of creating meshes. It's usually the longest time that you spend on CFD simulation. The solver then is just running on a computer while you're either away over the weekend or something like that. But in FlowFD, the meshing is completely automatic. So while the mesher runs maybe for a few minutes or hours, you can basically work on other stuff and you don't have to sit manually on creating the mesh. Then coming to the FlowFD technology, well, we're not doing any witchcraft. We use partial differential equations just like any other CFD tool as well. But we have a special meshing technology. First, we're using Cartesian mesh. There are 2 reasons for that. First, it's very simple to create. It's just an X, Y, Z direction, some blocks. But also it's very good for the automation. The second point is because the numerical equations are in X, Y, and Z direction, it's the most accurate one. If you have any cells going looking more wedge shape in hexahedral cells or tetrahedral cells, you have issues that you have approximations into the normal face coordinates direction. directions. So in this way it goes all in X, Y, and Z direction, and there's no approximation errors there. But we also use analytical and sort of theory equations in our simulation, as well as empirical data. This is necessary for areas, for example, where you don't resolve the mesh or the regions where you don't resolve it in detail with the mesh. So in reality, you cannot calculate that in a 3D simulation for the traditional CFD tools. This is where we basically apply analytical approach or empirical data. That can be, for example, a very small gap between heatsink fins, where we basically apply a one-dimensional approach, and you get the heat transfer as well as the pressure loss from that without resolving it in detail, and therefore saves a lot of cells. Usually we are below the number of cells that the traditional CFD tools have, and therefore it's a faster CPU time in most cases. But in general, it's about the same CPU time. It's really more efficient and easier to use in the whole process. Now here's a larger picture of an integration in CATIA, where you can see, for example, a mesh, and as it gets closer to the geometry, it refines. In smaller gaps, it will get a little bit finer. You can see the airflow coming here onto the front lens of this automotive headlight, where the housing is basically hidden, and you see the airflow, how it moves around. So this is basically what you can do in visualization, but you can also get numerical data out of points, surfaces, or over the transient simulation, how it behaves basically. Now, coming to the lighting specific capabilities, FlowFD has special modules specifically for certain applications, because not everyone needs all the capabilities. So we said we create a few modules that makes it a little bit more specific to certain applications. One is the LED module. It comes with a Monte Carlo radiation model. It also has a DO radiation model, but the Monte Carlo one is the most accurate and most widely used radiation model for lighting applications. You might know it from optical simulation. They also use Monte Carlo radiation model. But most CFD tools have a band-based radiation model. That means you have to specify specific wavelength bands. And within this band range, the values such as absorption, reflection, or refraction, they are basically averaged. And if the band is not accurately defined, that can cause an error in the averaging, and therefore cause an error in the results of the simulation. And therefore we also created the ray-based model, where each ray has basically one wavelength. That you might need more radiation, more rays, but it's just CPU time at the end. It doesn't need as much time as specifying the bands in very detail. Then, as I mentioned before, it's wavelength dependency, so multiple parameters such as refraction, absorption, and reflection indexes or coefficients, they are dependent on the wavelength, and this is something that you can represent with the Monte Carlo radiation model, as well as the DO. And of course, we are looking into lighting applications where the light of an LED has a distribution over the angle. So the intensity is depending on the angle that you look onto it. And we implemented that in the latest version of FlowFD, as well as radiation visualization. So you can visualize the rays as they, well, kind of move through the model. We have an LED thermal compact model, which basically consists of multiple parameters such as luminous flux, optical power, as well as the junction case thermal resistance, as well as capacitance. You can enter them manually from data sheets if you have them available, but we also have a measurement equipment, which I show a short slide later, where you can get all this information and directly load it into FlowFD by importing the file that the system, the measurement equipment exports. And of course the 2 resistor model for the LED, which you can get usually from every data sheet, the RTH value. Condensation and icing is also an interesting topic, especially if you have lights either built in like the floor outside, where you have spotlights coming out of the ground, you have water film from the condensation, or even ice, and you can really analyze how fast that is evaporating or melting, and how fast it basically freezes over when you shut it down. So this, for example, is one case where you can see how the evaporation of the water film at the beginning is evaporating to the edges, and there's a small sealing gap where you also can see how that is then a little bit later starting to evaporate. Then there's a Flow EDA bridge module that basically enables you to import PCB copper traces in all the detail, like you can see here in the picture. We have this copper trace for which the through connectors here are part of it, and there will be a chip on top. So you have a much better heat spreading simulation in such a CFD simulation than if you just apply a simple block where you might not have in detail the copper traces. You can select how many or which copper traces are most important for you for the heat spreading, so you don't have to import every single trace, but that's very important for some of the applications where you have not just a metal core PCB, but more of a spreading through copper traces. And the FlowFD electronics cooling module, you can here simulate Joule heating, which you can see here in this power switch. So you have, let's say, 1,000 amps coming in here and leaving here. You can see where the power switch basically has a contact. There's a very small surface compared to the rest of the power switch. So they have a very high current density, and therefore, as a lot of energy is released here into heat, basically it can really melt together in this case. And that's some case where you might have analyzed the fixture that was mentioned before in this liability or warranty case. There's a two resistor model as well for chips and a Delphi model in this module, and or better said, the Delphi model is part of the Flow EDA module, but you basically need the electronics cooling module to really have a more detailed electronics cooling simulation. Any standard component and material database, such as the electric properties of materials, as well as fan database and so on. For the radiation model, we can look at a model like this, where you have a surface or solar opening, basically sun coming in, shining in over through a lens and on a screen. There are three models in FlowFD. The DTRM, discrete transfer model in FlowFD, is the standard model. So if you don't have an LED which creates a lot of optical radiation in the visible light, so just a slightly glowing LED which is not really getting a lot of heat off in the optical spectrum, then the DTRM model is very well suited. It can do some focusing, but it is only suitable for solar radiation. It doesn't have any absorption inside of the lens, so you get a good focus for solar radiation, but no absorption, and therefore there's a little bit of higher energy reaching the screen as compared to when there would be some absorption in the lens. The DO model, even in a very high or the highest resolution of level 7 and second order accuracy, you don't get a sharp hotspot like in the other one. You get this kind of blurry spot. That's why the DO model is not very good for lighting applications, especially if you have any reflector or lens that is focusing. So the focusing is not very good. You have a band-based radiation model, so there's no very detailed distribution over the wavelength, but there is a wavelength dependency. And then the Monte Carlo model, which is the most accurate one. In this case, there were only 1 million rays used, so it's a little bit of noisy, but you can simply increase the number of rays. You get a more smoother plot like this, and less noisy in this way. It has the best focusing capabilities, including the absorption, and of course band and ray-based wavelength dependency. Now, other radiation features, such as mentioned before, the ray visualization. For example, here you see the bulb basically is radiating out all these rays that were calculated. Those are only a few of them visualized. So you can select how many you want to visualize. And for this example, it's very interesting. If you have any hotspots somewhere caused by radiation, you can visualize where this ray, where the light basically comes from that heats up the spot. And therefore see very nicely, okay, which surface maybe of the reflector has a slight angle that puts all the radiation onto that spot. And the refractive index dependency on wavelength as well as temperature. So you can create very nice pictures like this from the dark side of the moon from Purple Rain album here, where you can see really, depending on the wavelength, how the refraction index looks like. and you get this nice picture, as well as, and of course, in solar radiation cases where they have the xenon lens, like in a headlight here or anything like that, you can see how much of the spectrum in different wavelengths you can really reflect into which direction. So the spectrum really causes different hotspots depending on the wavelength. Another feature we just released is the radiation intensity, which I mentioned before. So this, for example, is a datasheet screenshot here, where you can see the LED basically has a radiation intensity in this kind of angular distribution. And another side of the plot is basically plotted over just the angle instead of a polar coordinate system in a Cartesian coordinate system. That's basically something that you can ideally take out the points, put it into the database of FlowEFD, and be used in this kind of simulation then as a radiation source. The other thing, of course, you want to specify a spectrum. So for example, if you have red LED or a blue one or a green one, they have different spectrums, as well as, for example, a laser, which usually has a very, very sharp needle like spectrum. You can specify the spectrum also as a radiation source. And for those of you who are working with UV LEDs or UV radiation to, for example, use in UVGI, so ultraviolet germicidal radiation, you can analyze the irradiation or the effective germinal dose here, in this case where the flow comes in from the left side, leaves the right side, and you have the UV lights up here. You can see this is basically the box down here. Where you can really see over time, or as the fluid, as the liquid basically moves through here, how it is then irradiated by the UV light and how efficient it or effective it was. Okay, coming to the FlowEFD presentation. Let me just switch to FlowEFD here. Where is it? Here. So this is the ProEngineer user interface, and I'm going to load a model which I have here. You can see there are a few variants already predefined. So I'll take this one, which has 11 fins in the replacement bulb. So the model here is basically a ceiling lamp. So we have the top ceiling here on the top, and the bulb is basically built into the ceiling in between. So you have the reflector here on the back, and the replacement bulb is sitting in the center. So let's make a cut here. You can see here there's a bulb built into that reflector, basically screwed at the end where the power connector goes then into the ballast somewhere, or the driver. But let's look at the model in more detail. So we have several small LEDs here, just represented here as a small cylinder. They can have any shape. You can sometimes download them from the website of Osram and Philips as a small CAD model. You can use them directly. In this case, it's really just a small cylinder here. We have a PCB material, the green material here, as well as a copper base for the heatsink, and then these fins here, which we have 11 in total, and yeah, the plastic basically housing around it. In our case, the FlowEFD, you can see the menu here is directly as part of the tab in ProEngineer. So you get all the boundary conditions, such as, in this case, epoxy resin housing. You have the copper base, and the LEDs in this case are represented as a copper and a heat source. But you can also easily create the LED component. You can see here's a tab for the FlowEFD analysis, and we can simply select an LED feature, and when we zoom into the LED, we would select the LED as a body, select the bottom surface, basically heat conducting surface. That's the wrong one, sorry. This one. And the top surface, which is basically illuminating surface. You have now the chance either to select a 2-resistor model. Let's go into the database to show it in more detail. For example, we have the two resistor model here where you just specify the junction base thermal resistance. You can also activate junction top, but usually in LEDs that's not necessary. Or you specify one of the, no, come on, go out of here. Or you specify one of the predefined ones where you can see there's much more data behind it. Voltage sensitivity, radiant flux and radiant flux sensitivity, luminous flux sensitivity, as well as the thermal resistance, thermal capacitance of the LED. Now, some of the data you can get from the data sheet, others like the thermal capacitance usually not, but you can also simply apply thermal resistance and the other properties which you usually can get from the data sheet and manually input that. If you create your own LED and you have the measurement equipment that we also provide, then you can simply select you want to use our C-ladder model and then import that from the Tristron Terralet, which is the measurement equipment. This is the most accurate version because you will be able to analyze the junction temperature and see directly the hot lumen of the LED based on that junction temperature. Because usually when you apply a heat source, that is actually depending on the temperature of the junction because the voltage is changing on the temperature, and therefore there's a small variation in the voltage in total and therefore also in the heat losses of the LED. We have radiation properties on surfaces here, material properties, a heat source onto the LED, and contact resistance such as tin material or something beneath the LED that increases the thermal resistance a little bit compared to pure contact, but in reality, as we all know, the contact is not pure, it's kind of a rough surface, so you want to improve that by applying a very high conductive or thermal conductive contact material to material. Now, looking at some of the results here, quickly loading them in here, you're able now to create plots, streamlines, everything that a traditional CFD tool can do as well. As there's no witchcraft in creating some nice pictures. So let's have a look here on, for example, there are some plots already defined. Let's take this cut plot. Basically it shows you here how the air is moving through the lamp as well as on the outside of the lamp to the environment. You can see how it hits the surface of the roof and then or the ceiling and then moves to the outside, and it basically kind of has a circulation on that. We can also look at not the velocity, but for example the fluid temperature. You can see that of course near the LED the fluid is hot, as well as then in the area of the heat sink above the copper plate, and on the outside it's heating up at the reflector a little bit, moving upwards. That's why you have the natural convection case here. You can also use fans if you have like high power LEDs, for example in stage lights. That's of course no problem. There are enough fan curves, but you can also, if you design the fans yourself, have them really actually rotating and causing the airflow. Now, yeah, post-processing capabilities, I mean surface plots, let's have a look on this one here. You can create so many possibilities of making something visual that you usually don't see, which helps you then at the end again of increasing the ability for you to decide where you want to improve the geometry, how you can improve it, and much better decide the parameters that you want to improve. Any number of fins or distribution of the fins, the thickness of the fins, and so on. Okay, coming back to the PowerPoint. So just quickly going to the measurement equipment. As I mentioned before, this is Terralet, basically the sphere and the first box here. Tristor is the bottom box. It measures the thermal resistance, so thermally, as well as radiometrically, so color coordinates, luminous flux depending on the current that you apply as well as the temperature of the LED, because you can control the temperature. There is a cold plate at the end, or really can control the temperature. And that all according to the JEDEC standards, which we were part of creating them. So this thermal transient measurement can be used for Q&A evaluation. For example, if you buy an LED from a no-name Chinese vendor or from Osram and Philips, you can really find issues such as in this case, where you have a brand new LED with a low thermal resistance, and once it reached 500 hours, it already has almost doubled the thermal resistance. And those are the cases when you have your LED thermal management not matching the original LED anymore. The LED thermal management that you created was basically for this LED, and it is completely a different LED at the end after it has aged. So some LEDs from some vendors are much more stable. They age a little bit like this here, but not as much as this, and therefore the thermal management would not be suitable anymore. From that measurement, we can create a thermal compact model, which is then used in the thermal simulation of FlowEFD. So coming to the conclusion, we want to avoid thermal and thermal-related warranty and liability issues with CFD simulations. And the CAD-embedded CFD approach is a very fast design cycle, because you're directly working in the CAD system, you can test every idea that you want to do, like different heatsink shape, forms, or number of ribs, thickness of ribs, as much as you like. It's just up to you how much you want to spend in simulation time until you get to the final thing, to the final design. You can use parametric studies, optimization tools, really very effective simulation system. Yeah, the CAD embedded is CAD embedded into the most major CAD systems, as well as it is the most advanced CFD solution with the most lighting relevant simulation features that is on the market. You can't find any other CFD tool that has that many features as FlowEFD. Now, if you want to see more information about some examples, there's, for example, one article in our Engineering Edge magazine about then a street lighting model. Another one is from a replacement bulb. That was written by one of our engineers, but back at the time when he was working from one of our customers. So this model was based on a paper that he was doing while he was still working with his previous company. And there's also an online kind of a cloud version where you can test it for 30 days. There is an LED case, like I just showed the LED bulb, where you can play around with it and see on yourself how well it is working. But also you can contact FreeHDI and work with them to do an evaluation, do a benchmark, and really find out how it can help you in your design. Okay, that's it for my point. I think we're now ready for questions and answers.
Boris, I think you did a fantastic job. Thank you. I think that was, I don't want to say self-explanatory, but it was very easy to understand. One of the reasons we're excited about FlowEFD is simply because it's, like you said earlier, it's putting the analysis capabilities in the hands of the designer, so that it's the designs, if they go downstream to an analyst, they're basically being verified as opposed to having to come back to the designer. And if a company doesn't have an analyst on site, that this becomes their analysis tool. And there's a specific customer who, when earlier this year, when they purchased FlowEFD, were kind of amazed. It's almost like they had known about it. We had been talking to them about it, but then it finally just clicked, and they're like, and their approach was, or their response was, wait a minute, because we're spending about a month. It literally was a month for them to run an analysis on a product that they were making, and they were blown away at the fact that they could get it done within half an hour at some point. Sometimes it's 45 minutes, sometimes it's a half an hour, but what's amazing is that amount of time savings, and at that point it became a no-brainer. So hopefully this information is helpful today, and as Boris said, if you want to get in touch with 3HTI to hang on, I'm kind of shifting gears here. Make sure you guys are seeing the right screen. Okay. If you want to get in touch with us, hang on. Sorry about that. Our phone number is 866-624-3HTI. And you can email us at info@3hti.com, and there's my personal information as well if you want to contact me directly. We'd be more than happy to help you guys out. So there are no questions at this time in the queue. However, people are saying thank you, great presentation. I agree, Boris. I think you did a fantastic job, and I think it was very knowledgeable and very informative. So if there's no questions at this time, or if you have any questions afterwards, if you think of something, feel free to email me or email us at 3HTI or give us a call. So Boris, once again, thank you. Thank you for the Pink Floyd reference as well. I thought that was, that was definitely entertaining. It's good to have a sense of fun with these things also. So I want to say thanks again, and everybody have a great afternoon. Take care.
Thanks,
Boris.